Exam 3 review. It starts with the oxidation reduction reactions, and in this part you have to be able to find the oxidation state of elements, and you have to be able to find what is oxidation state, oxidizing agent, and what's reducing agent. So the first question is to find the oxidation state of elements. So A, we want N in NO. So there were certain rules in the lecture slides that you have to know. You should know that the neutral molecule, the sum of oxidation state of all elements are 0. And if you have a polyatomic ion, the sum of oxidation state of all elements equal to the charge of the polyatomic ion. So NO is a neutral molecule, and the rule says oxygen, most of the time it's -2, except if it's bonded with itself in peroxides or it's bonded with fluorine. In most of the cases, except these rare cases, the oxidation state is -2. So to find the oxidation state of nitrogen, you know the sum is 0, so you have one oxygen, so nitrogen plus -2, which is the oxidation state of oxygen, equals 0. So the oxidation state of nitrogen should be +2. And B in NO2, the same thing. So you have nitrogen plus you have 2 oxygens, and each of them is -2, so it's 2 times -2 equals 0. So N should be +4. C, Cr in Na2Cr2O7. So oxygen, O is -2, most cases, also in this one. Ions, like metals, the oxidation state equal to the charge of the metal. Chromate is a polyatomic ion that you have to know. The charge, it's -2, and even if you don't know that, sodium is in the first group, is in group 1, so the charge of the group 1 metals always +1. So the oxidation state of sodium is +1, oxygen is -2. To find the chromium, you set up the equation. You have 2 Cr, so 2 times +1 for sodium, 2 times Cr plus 7 oxygen, 7 times -2 equals 0, and you find the oxidation state of chromium as +6. The same thing for D, phosphorus in phosphate. So P in PO4 3-. So as I said, polyatomic ions, I write the part D and E up in here. So that's E, and this is, I'm sorry, that's D, and this is E. So P in PO4 3-. So in polyatomic ion, the sum of the oxidation state equal the charge of the polyatomic ion. So P plus 4 oxygen, and oxygen is -2, so 4 times -2 is -8, equal the charge, which is -3. So P, phosphorus, oxidation state should be +5. And the same one in the last one, C in CO3 2-. The sum equals to the charge, -2, and C plus 3 oxygen, which is -2, is -6, equal -2, so C should be +4. So that's how you find the oxidation state of the element. Okay, so how do we use this to, I have to erase that, it's just coming down. So let me erase this. Okay, how do we use this to find what is oxidizing agent, what is reducing agent? Next question is, what element is undergoing oxidation, and which one is going reduction? So I told you this in lecture slides. You can either use the Leo-Gehr or oil rig or whatever works for you. For me, the one which is easier is if I have a reduction in the oxidation state, that thing is reduced, if there is an increase in the oxidation state, that is oxidized. Okay, so if we check the oxidation state of these elements, hydrogen in most cases is +1. If it's with metals, it's -1. In all of these compounds here, it's with non-metal, so it's +1. So nothing happened to hydrogen. Oxygen, if you see in the reactant side, it's in the standard state, O2, so it's 0. But in the product, it's with carbon, so it's -2. So we have 0 to -2, it's going down, so it's reduced. Okay, so what is oxidized? So we have only 3 elements in this reaction. We have oxygen, hydrogen, and carbon. Okay, we just discussed about hydrogen, that nothing happens to hydrogen, it's +1 on the reactant and on the product. Oxygen is reduced, so carbon should be oxidized. But to double check, we'd find the oxidation state in carbon, for carbon in the reactant. It's CH4, so the sum should be 0, and H is +1, and we have 4 of that, so C plus 4 equals 0, so C oxidation state is -4. In reactant side, it's carbon is in CO2, carbon is in CO2, so oxygen is -2, and we have 2 of that, so C plus 2 times -2 is -4, and that equals 0. That makes oxidation state of carbon in CO2 as +4. So we are going from -4 to +4. So we have increase in oxidation state. So the increase, when you have increase, it's oxidation. Okay. So what is oxidized? Carbon is oxidized. So the answer is C. And I try to write that in a chart here on the right, so that makes it easier. From 0 to 2, -2 is reduced. From -4 to +4 is oxidized. Question number 3, what element is undergoing reduction? So again, zinc, Zn, is in standard state, solid form, so the oxidation state is 0. If it's an ion, the oxidation state is the charge of the ion. Okay. In the reactant, we have zinc as solid, so the oxidation state is 0. And we have silver nitrate, so nitrate is -1, and silver should be +1, so that the oxidation state of Ag, silver, is +1. In reactant side, in product side, you have zinc nitrate, and you see you have 2 nitrates, so you have 2 -1, so zinc should be +2. Okay. So the oxidation state of zinc in the product is +2, and silver, on the other hand, is solid silver, so it's the oxidation state is 0. Okay. And nitrate is nitrate, so nothing happened in nitrate, so you don't even need to check for the oxidation state of nitrogen and oxygen. You don't need to do that. Okay. It's a polyatomic ion, both in the reactant and product, so the oxidation state should not change. It should be the same thing. Because we have a different state for silver and zinc, the oxidation state of these two will change. So zinc is going from 0 to +2. So you have increase in oxidation state. So zinc is oxidized. For silver, you're going from +1 to 0. So it's going down. It's reduced, it's decreased. Okay, so when you have a decrease in oxidation state, the element is reduced. Okay, so what element is undergoing oxidation? Silver, Ag. So next question, question number 4, is asking what is the reducing agent. Okay, so you have to be careful with these things. With these two terms, we might say silver is reduced, but we might ask what is the reducing agent. Okay, when you're asking about the agent, reducing agent is something that reduces something else. Okay, because that's reducing agent. Its job is to reduce other elements. Okay, in order to reduce something, that element needs to oxidize itself to reduce something else. Okay, so when something is oxidized, you have increase in oxidation state, you lose electron. When you lose electron, the electron does not just go away, it has to go to somewhere else. Okay, so because you're donating electron to something else, you are oxidizing the other elements, and when I say you, I mean the element. So the element is reduced itself. Okay, sorry, oxidized itself. So it's reducing something else and it's oxidized itself. Okay, so a reducing agent needs to be oxidized itself. Okay, so whatever is oxidized is the reducing agent. Whatever is reduced is oxidizing agent. Okay, so that's a little bit confusing, but if you think about it, what agent does, so when you say reducing agents, because it's an agent, you have to do that job for other people. Okay, I've heard this example, I don't know if it helps, like actors have agent, and the agent is not going to do the acting job, it's just going to find the acting job for the actor. Okay, that's what the agent does. So with the same analogy, reducing agent is something that reduce something else, and it needs to be oxidized itself. Okay, so again, we need to find what is oxidized and what is reduced, and then we can see what is reducing agent and what is oxidizing agent. So lithium is in the solid state, uh, so its oxidation state is 0. Iron is making an ionic compound with acetate, and acetate is -1, so, and we have 2 of that, so the oxidation state of iron, Fe, should be +2. On the reactant side, we have lithium acetate. Again, the same logic. The oxidation state of lithium is +1 and acetate is -1. So again, we do not go through carbon, hydrogen, and oxygen because it's an acetate ion in both in reactant and product. Nothing changes. Okay, so if you can go ahead and find the oxidation state of all 3 of them, but you don't need to, because we are looking for a change, right? If nothing is changed, you have the polyatomic ion both in reactant and product, you don't want the headache. Okay, just leave it there. Okay, so check for the oxidation state of the other things. So we check for the oxidation state of iron, it's +2 in the reactant because it's a +2 charge ion. In the product side, you have lithium acetate, so you know the charge of the lithium is +1, so the oxidation state is +1. And the iron is in solid state, so it's 0. It's the standard state, oxidation state is 0. And the standard state for iron is iron metal, solid iron metal. Okay, so for lithium, we are going from 0 to 1, so we have increase in oxidation state. So lithium is oxidized. Iron go from +2 to 0, so it's going down, so it's reduced. Okay, so iron is reduced, lithium is oxidized. What is reducing agent? So we said reducing agent is something which is oxidized itself. Okay, which one is oxidized? Lithium is oxidized. Okay, so since lithium is oxidized, that's a reducing agent. Okay, so the answer is lithium. The other thing you need to know for reducing agent and oxidizing agent is that when we say agent, we are not talking about just the elements. Okay, so reducing agent is the whole compound. For this example, it happened to be the solid lithium, but if I was asking what is oxidizing agent, your answer shouldn't be Fe, because Fe is just a metal, because Fe itself cannot do anything. But Fe, iron acetate, the whole compound, is the oxidizing agent. Okay, so when we say oxidizing agent, I want you to put the whole compound, ionic compound. But if I say what is reduced, the iron is reduced, the element is reduced. Okay, So that's the difference between the agent and when we say what is reduced and what is oxidized. Okay. Next question, question number 5. How many moles of oxygen are formed when so this is stoichiometry. So we passed through the redox reaction and we are starting the stoichiometry. And with the stoichiometry, we have limiting reagents, percent yield, everything mixed together. Okay. So we start with the stoichiometry, and stoichiometry is a relationship between the moles in a balanced chemical reaction. So when you want to relate two compounds in a chemical reaction, you need to go to the mole bridge. Okay, you cannot relate things without moles. Okay, so it's good to map out what I do under the chemical reaction for yourself. It helps not to jump from mass to mass or anything else. You have to know that you have to go to the mole, use the mole bridge to go to whichever compound you need. It might be, I don't know, reactant to reactant or reactant to product, product to product, doesn't matter, okay? Whatever compound you have in your chemical reaction, you can use that mole bridge to go to the other compound. The only thing you should be careful about is that the reaction should be a balanced chemical equation, and you use the coefficient as the molar ratio of the two compounds. Okay, so how many moles of oxygen are formed when 58.6 gram of potassium nitrate decomposes according to the following reaction? So you have the mass of the KNO3 potassium nitrate. You need the moles of oxygen. Okay, so you cannot go straight from mass to mole of oxygen, but what you need to do is going to the mole of the same compound, then you can use the mole bridge to go to the mole of the other ones. So the first step is going from mass to mole of the potassium nitrate, and the second step is going from mole to mole of oxygen. So we use dimensional analysis. We start with a given information, which is the mass of KNO3, and the first step is using the molar mass to go to the mole. So molar mass is the amount of mass in 1 mole. So I want to get rid of the mass, the gram of KNO3. I put the gram on the denominator, and the numerator is mole of KNO3. So 101.11 gram of potassium nitrate is 1 mole of potassium nitrate. But I don't want the mole of potassium nitrate, I want the mole of oxygen. So then you can use the mole bridge, you can use stoichiometry to go from mole of KNO3 to the mole of oxygen. So if you see the coefficient in a balanced chemical equation, we have 4 KNO3 and we have 5 O2. So it means that 4 mole of KNO3 equals 5 mole of oxygen. So I want to get rid of mole of KNO3. I put the mole of KNO3 on the denominator, and the numerator is mole of oxygen. So we are good with the units. The rest is just putting these numbers in your calculator and find the number. And that's 0.724 moles of oxygen. Okay, so second page, question number 6. According to the following reaction, how many grams of sulfur are formed when 37.4 gram of water are formed? So sometimes, most of the time, you get reactants and you'll be asked from product, but this question is a good one, so you should know that it's not always the case. You can use stoichiometry to relate anything in a balanced chemical equation. You can go from reactant to reactant, you can go from reactant to product, you can go from product to product, and that's the case in this question. So you are given the mass of one of the products, and it's asking you the mass of the other product, okay? So that's still the same thing. You can use stoichiometry. So you have the mass of water, you want the mass of sulfur. So you cannot go directly from mass of water to the mass of What you need to do is to go to the mole, use the mole bridge, go to the mole of sulfur, and then from mole of sulfur you can go to the mass of sulfur using the molar mass, right? So 1, 2, 3, three step. You start with the mass of water, which is given. Use the molar mass of water. You want to get rid of gram of H2O, so you put the gram of H2O on the denominator, and mole of the water on the top. And then the next one using stoichiometry, so you see the coefficient, the balanced chemical equation, 3 sulfur and 2 water. So 2 moles of water equal 3 moles of sulfur. So that's your second step. And the third step is using the molar mass of sulfur, which is 32.065 gram of sulfur is 1 mole of sulfur. So we can get rid of mole of sulfur and end up with a gram of sulfur. So since the units match the units match the answer, so the rest is just putting these numbers in your calculator and find the answer, which is 99.8. Okay, so next question, you have the density of ethanol. How many milliliter of ethanol are needed to produce 30 gram of CO2? So you have the balanced chemical equation, you have the mass of the product, now you need the volume of the reactant. Okay, so as I said, stoichiometry, relationship of the moles in a balanced chemical equation. Okay, so whatever you want to do not go from mass of one compound to the mass or mole of the other compound. You need to use the mole bridge. Okay, always mole to the mole. So the first step is going to the mole of the given compound. In this case, it's a product. We can go to the mole from mass of CO2. We go to the mole of the CO2. Then the second step, we use the mole bridge, going from mole of CO2 to the mole of ethanol. And then from mole of ethanol, you go to the mass of ethanol. The question is asking about volume, and the density is given, and density relates, that's one of our conversion toolbox, right? So density is the relationship between mass and volume. Okay, so we want volume. With density we can get the volume with the mass. Okay, so first we go from mole to mass with molar mass, and then from mass we can use density to go to volume. Okay, makes sense? So step 1, 2, 3, 4. 1 is mass to mole of CO2, 2 is mole to mole of ethanol, 3 is mole to mass of ethanol, and then mass to volume. So starting with the given information, 30 gram of carbon dioxide, using the molar mass of carbon dioxide, going from gram to mole of CO2, then use stoichiometry, the coefficient, the balanced chemical equation. 2 mole of CO2 is 1 mole of ethanol, and then use the molar mass of ethanol. 1 mole of ethanol is 46.07 gram of ethanol, not methanol. And using the density tell us that 0.789 gram is 1 milliliter. Okay, so I don't want the gram of ethanol, I want the milliliter of ethanol. So 0.07 gram of 0.0789 gram of ethanol is 1 milliliter of ethanol. And what is the question asking? How many milliliter? Okay, so that's what we have. So the unit is fine with what is asked on the question. So you put these numbers in your calculator and find the answer, which is 19.9. Next question, how many grams of HCl can be obtained from 60 gram of BCl3 and 37 gram of water? So when you have two mass for the reactant, when you see 2 mass for the reactant, you know you're dealing with a limiting reagent problem. Okay, because when you have the mass of both of them, one of them should be in excess and one of them is the limiting reagent. So what you need to do is to use both of these two reactants and see how many products you make. Okay, the one that gives you less product is the limiting reagent. Okay, so the same map I draw for all the uh, reactions. So the first step is going from mass to mole, then from mole to the mole of product. That's step 2. And the third step is to going from mole to mass. So I mentioned this in the lecture slides, or maybe in the worksheet, I don't remember. But to find the limiting reagent, you don't need to go to the mass of the product. Even mole of the product should tell you which one is the limiting reagent. But since the question is asking about the gram of HCl, I would do that for both of them. So when I find the limiting reagent, I already find the final answer. But it's okay if you want to find the number of moles and then see which one is the limiting reagent and then use that number and then convert it to the mass. That's also fine. It's up to you. Okay, but I prefer to do all these steps in one line using one-dimensional analysis and then find the answer. It's up to you. So that's what I did. So I started with the mass of both of the reactants. I had 60 gram of BCl3 and 37.5 gram of water. So the first step, going from mass to mole for both of them. Second step is going from mole to mole of the product using the coefficient in a balanced chemical equation. And the last step is using the molar mass of HCl to convert the mole to the mass. So 60 gram of BCl3 gives me 56 gram of HCl, and 37.5 gram of water gives me 75.9 gram of HCl. So one thing that you don't want to do is looking at the numbers in the question and say, okay, I have 37 gram of water and 60 gram of BCl3, so I have less water, so that should be the limiting reagent. No, never do that. That's very bad, because the molar mass of different compounds are different, and the coefficient in a balanced chemical equation is different, so you don't know how much product you're going to make. Okay, you have to do the calculation and see how much product you're making with each of these, and then you can decide based on that. Okay, and this is a good example that shows it's the opposite result. So 60 gram of BCl3 is more, but you see that that is the limiting reagent. Okay, so BCl3 is the limiting reagent, and 56.0 gram of HCl is your theoretical yield, or the mass of products you make with your theoretical yield. So the answer is 56.0 gram of HCl. Next question, question number 9. How many moles of excess reactants remains from the reaction of 3 moles of C8H18 and 3 moles of O2? Again, you have two amounts, moles or grams, both of them would be the same thing. We have two amounts for the reactant, so that's a limiting reagent. Even if we don't know that, the question is asking about the excess reactant, so there should be a limiting reagent to find the excess reagent, right? So what you need to do is to find how much product you make, and then you have two products. You can choose one of them, it doesn't matter. Okay, you can choose CO2 or water, both of them should work. Just choose one of the product and see how much product you make. The one that gives you less product is the limiting reagent. And in this question, it doesn't ask about the mass of product, so that's one of the things I told you before. You don't need to find the mass of product to see which one is limiting reagent. As long as you find how much product each of them make and with the same unit, you can decide which one is the limiting reagent. So I go to the mole of the CO2 and then I can see which one is the limiting reagent. Okay, so 3 moles of C8H18. I have the mole. I want to go to the mole of CO2. So the coefficient is 2 mole of C8H18 equal to 16 mole of CO2. Okay, gives me 24 mole of CO2. The same thing with the oxygen. I have 25 mole of oxygen make equal to 16 mole of CO2. That gives me 1.92 mole of CO2. So oxygen is giving me less product, so that is the limiting reagent. So now I want to know how much of the excess reagent remain after the reaction is complete. Okay, so I have to see how much of the C8H18, I'm sorry, C8H18 is used up, and then you can subtract from the initial to see how much is left. Okay, so with 3 moles using stoichiometry, 3 moles of oxygen, I'm going to the mole of C8H18. Okay, so 25 mole of oxygen equal 2 moles of C8H18 equals to 0.24 moles of C8H18. So that's the amount of the reactant which is used up. Okay, so for 3 moles of oxygen, 0.24 mole of C8H18 is used up. So how much of the excess reagents remain? So initially you had 3 and you used up 0.24. So how much remain? You subtract these two, and 2.76 moles of C8H18 remains. Okay. Okay, next one. So it's asking for the percent yield, and percent yield is the actual yield divided by the theoretical yield times 100. The actual yield is something that you will be always given most of the time, or if you don't have the actual yield, usually you have percent yield, and the question is asking about the actual yields. Okay, so you should have one or the other. You should, in the question, you should have actual yield or percent yield. But for the theoretical yield, you can find it by stoichiometry and doing the calculation. Okay, so in this question, it's asking for the percent yield when this amount of CO2 is formed. So you have the mass of the product in the question, and that is definitely the actual yield. Okay, so that is your actual yield formed from the reaction of 8.5 moles of 8.5 moles of C8H18 and 16 moles of O2. Okay, so what is theoretical yield? Theoretical yield is the maximum amount of product you can make based on limiting reagents. Okay, and you have two amounts for two reactants, so you have to find the limiting reagent first. So this question is a mixture of limiting reagent, stoichiometry, and percent yield. Okay, so I need to find the theoretical yield, and theoretical yield is the mass of product based on the limiting reagent. So I find the mass of CO2, that's what I'm trying to find the percent yield on, because I have the actual yield of CO2. So I'm trying to find the theoretical yield for CO2, so I need the mass. So I use stoichiometry, going from the mass or mole of both of the reactants, the C8H18 and oxygen, and going from the mole of that to the mole of product, and from the mole of product to the mass of product, which is step 2, to see how many grams of carbon dioxide I get from these two amounts. Okay, so 16 mole of oxygen gives me 450.7 gram of CO2. 8.5 moles of C8H18 gives me 2,993 grams. So the one which gives you less product is the limiting reagent, and the mass from the limiting reagent is the theoretical yield. Okay, so oxygen is the limiting reagent, and this 450.7 gram of CO2 is the theoretical yield. To find the percent yield is actual, which is taken from here, divided by the theoretical times 100, and that's 28.6 divided by 450.7 times 100 is 6.25%. Okay, next question. 13 gram of calcium metal is reacted with water. 5 gram of calcium hydroxide is produced. So when you have a mass of product, and if you read the rest is asking for the yield, percent yield, you know that the mass of product in the question is the actual yield. Okay, so the mass of calcium hydroxide 5 gram is the actual yield. It's asking for the percent yield, so we have to find the theoretical yield, and the theoretical yield is the mass of product based on the limiting reagent. So in this question, since there is only one mass for reactant, you don't need to find the limiting reagent. You just assume that that is the limiting reagent. Sometimes we mention the question that this amount of, in this case, calcium metal is reacted with excess water to emphasize that water was in excess and calcium was a limiting reagent. But anyway, if you have only one answer, one number for the one mass for the reactant, you just find it based on that one mass. So you start with the mass of the reactant, go to the mole, then use the mole bridge, go to the mole of calcium hydroxide, and then go to the mass of calcium hydroxide, and that's your theoretical yield. So that's what we did here. Step 1, going to the mole. Step 2, using stoichiometry, 1 mole to 1 mole, and using the molar mass of calcium hydroxide to find a gram of calcium hydroxide, and you get 24.0 gram of calcium hydroxide, and that's your theoretical yield. So your actual is that 5, so 5 divided by 24 times 100 is 20.8%. Question number 12. Percent yield for the following reaction is 65. So in this question you have percent yield. So when you have percent yield, definitely you need to find the actual yield. So how many grams of KClO3 are needed to produce so you have the actual yield basically. So you both have the percent yield, and if you have the mass in the question, that is your actual yield. So you have the actual yield, you need to find the mass of the reactant. Okay, so you know that with these two you can find theoretical yield, right? Because the equation says actual over theoretical times 100 is percent yield, right? So you have percent yield and you have actual yield. And how, so one dark spot, that's what I call it, dark spot, the things that students usually do not look at, or the dark area that usually students are confused. So how do we know that this number is the actual yield? So usually the number, if you're talking about percent yield, if the question contains percent yield, usually the number in the question, if in the question we say 4 gram of oxygen, and that's a product, okay, most cases when we say the mass of the product inside the question and we are dealing with a percent yield, that number is the actual yield. Okay, so just take that. So the mass of the product in the question in the percent yield problems is the actual yield. Okay, so you have the actual yield, you have the percent yield, you can find the theoretical yield. When you get the theoretical yield, you can use stoichiometry. Remember, for using the stoichiometry, you cannot use actual yield. Okay, it should be theoretical yield. You cannot find the mass of reactant or use any kind of stoichiometry with actual yield. So when you get the actual yield and percent yield, find the theoretical yield, and that's what I did here. So actual divided by the theoretical times 100 is percent yield, and you set up this equation and you solve it, and you end up with 6.15 gram of O2 as your theoretical yield. So now you have the mass of O2, which is 6.5. You just get it from there, and then use the steps that we just discussed, going from mass to mole, use the mole bridge, and then going from mole to mass. And that's what I did. Step 1, step 2, step 3, and then boom, you have the mass of your reactant. The last the last question on this page, I guess, yes, 13. So how many milliliters? Oh, I think we just get into titration. Okay, titration is just like stoichiometry, still the same thing, but usually in stoichiometry and limiting reagent or percent yield, usually we are dealing with mass. In titration, we are dealing with volume and number of moles. Okay, so mole is the same even in stoichiometry. We use mole. So we are still using stoichiometry, but in titration, usually we are dealing with volume. Okay, so but it's still same thing. So in the previous part, we used mass and molar mass to relate mass to the mole. Then when we are in the mass highway or mass bridge, whatever you want to call it, you can go from one element to whatever element you want in the balanced chemical equation. Okay, that's, you just have to go to the mole. From mole you can go wherever you want. Okay, so in the stoichiometry we had mass and molar mass to get into the mole. In titration we have volume and molarity. That's the same concept. So you use volume and molarity to get to the mole. When you get to the mole, you can go wherever you want. Okay, so let's read the question. So how many milliliter of 0.26 molar sodium sulfide NO2S is needed to react with 35 milliliter of 0.31 molar silver nitrate? Okay, so we have the volume of silver nitrate, and the question is asking about the volume of sodium sulfide. Sorry. So again, the same concept. Step 1, going from volume of silver nitrate to the mole of silver nitrate. And how do we do that? Volume to mole, we use molarity. Okay, that's one of our toolbox. So molarity is used to go from volume to mole, or vice versa, mole to volume or volume to mole. Okay, so step 1, going from volume of the silver nitrate to the mole of silver nitrate, and using stoichiometry, mole of the silver nitrate to the mole of sodium sulfide with a coefficient of the balanced chemical equation. And then step 3 is using the molarity of sodium sulfate to go from mole to the volume. Okay, so we start with the volume of the silver nitrate. So volume of silver nitrate is 35 milliliter. So you know, molarity is mole over liter. So you should convert milliliter to liter, and I just did it with, we talked about this in the lecture slides. You can start with 0, no, not 0.0, let me erase that. Okay, you can start with 35.00 milliliter and then add one conversion factor. Say, okay, I don't want milliliter, I want liter, and I know that 1 milliliter is 10 to negative 3 liter, and then from that continue from to here. So you can put this here, right? Or we've done this a lot, so you know that simply if you move the decimal point 3 digits to the back, it's liter. Okay, so 35 milliliter is basically 0.035 liter of silver nitrate. If you don't feel comfortable with that, you can start with your milliliter and use a conversion factor to convert it to liter. Okay, so We start with that. We need to go from liter, from the volume to the mole, using the molar mass of silver nitrate, going to the mole of that, and then using stoichiometry with a balanced chemical equation. So 2 moles of silver nitrate equals 1 mole of sodium sulfide, sorry. And then from there, using the molar mass of NO2S to go from mole to the volume. When you go to the volume, molarity is mole over liter. Okay. So in this step, when you use mole, you got the liter, and the question is asking how many milliliter. Okay. So you have to do one conversion in the end to convert liter to milliliter. There was also one other way to do this. You could have used milliliter in the beginning, even though, so if I want to write milliliter, I would write 35 milliliter of AgNO3, right? Even though the milliliter doesn't cancel out with the liter of any AgNO3, but we need to have one conversion. If you think about, if you write this part, okay, so we have one conversion from milliliter to liter, and in the end we have another conversion from liter to milliliter. So these two cancel out together, and then you get a milliliter. So even though the milliliter of the Ag nitrate doesn't cancel out with a liter of silver nitrate, in the end this liter milliliter thing will cancel out. Okay, so you could have started with a milliliter and just keep it as milliliter, and the final step would give you the milliliter. But I thought that might be a little bit confusing, so I think it's better to just use liter, cancel out the units, and in the end convert the liter back to milliliter, just to be in the safe side. So that's how you do it, and your final answer is the milliliter of the sodium sulfide, and you put the numbers in the calculator, and that's 21.20. Okay, the final part for the exam is thermochemistry. So in thermochemistry, you have to know some definitions. You have to know what is system, what is surrounding. You have to know about the first law of thermodynamics. You have to know about the law of conservation of energy. And here are some problems that you might have in the exam. So one thing that you need to know is, when do we have negative or positive work and heat? Okay, so I said that in the lecture slides. Heat, when the system is gaining heat, it has an increase in energy, so the Q is positive. When it's losing heat, it's losing something, it's losing energy, it's losing heat, it has a reduction in temperature, and the Q is negative. Okay, for work, I can define it in many ways, but how it stick in my mind, it might not be relevant, or it might not make sense. I don't know. That's how I remember it, and I think it might be helpful for you. So system is lazy and doesn't want to do work. So if the system does the work, it's not something something that the system likes. So it's a negative work. If the surrounding does the job, if the surrounding do the work on the system, W is negative. Okay, so you get W is positive. So the system doesn't need to do anything, so it just laid back on the couch, and the surrounding do this work on the system, so the work is positive. Okay, so in this question, the system is doing the work, so it's negative work, so negative W, and it's losing heat, so losing heat, reduction temperature, Q is negative, so both of them are negative. So you just have to learn this. In the exam, it might be mixture of these things, so you have to know what is negative work and what is positive work, what is negative Q, what is positive Q. Okay, 15. Which of the following is true if delta E or delta U or delta E. It's the change in energy. Both they show them with both E or U. So delta E or delta U of the system is 260 joule. So you know that the energy, that's the conservation of energy, right? The energy is not destroyed nor it's created. So it's just transforming from different types to the other type, or going from one place to the other place. So we know whatever energy that the system is losing or gaining, the surrounding is gaining or losing. So they're in equal amounts with different units, different signs. Sorry. System and surrounding, and so if it's a positive delta U, it means the system is gaining energy. It's positive. So the system is gaining 260 joule energy, and the surrounding is losing the same amount of energy. So it's A. Okay, question number 16. To the rest is just using this equation, and that's the whole thing in not the whole chapter, but until we covered for the exam, for these 3 sessions that we had for this chapter before this exam, is all about this equation Q MCAT. Okay, so you have to know how to use this equation. So it's just as a matter of what we are trying to solve. We are trying to find delta T, we are trying to find Q, we are trying to find C, but it's all using this equation. Okay, so in this kind of question, I always write down a summary of the given information when you read the question. So the specific heat of copper is given, so you write C equal that. The mass of copper is given, M equal that. And the initial temperature, so initial temperature is T1 or Ti, so that's that. Absorb this amount of energy, so Q is given, and you have to be careful with the units. It's in kilojoule, so you have kilojoule, you have to convert it to joule. Okay, so we get our Q in kilojoule, and what is it asking for? The final temperature. So we're trying to find what is T2 or TF. Okay, so we have to find delta T first. So solving for delta T, it's delta T equal Q over MC. You just put in your numbers and find a delta T, and when you find a delta T is T2 minus T1. So you're solving it based on for T2, so it's delta T plus T1. So T2 is 381. So the same thing on the next question. You have the Q, the sample absorbs this amount of energy. So absorbs energy, you have to be careful with that. So it absorbs energy, so it's plus a positive amount for Q. So Q is plus 43.6. Okay, if it says it's losing 43.6 kilojoule of heat, then it would be a negative Q. Okay, so you have the Q. It says resulting in a temperature rise of, so it says the temperature rise, so it's already giving you the change in temperature. Okay, so you have delta T, so you have to be careful with these wording. So temperature rise of 50, so delta T is plus 50 degrees Celsius. It wants the mass in kilogram, and you have to be careful with the units, because what you get in this equation is gram, so you have to convert that in the end. And you also have the C. Okay, so again, C equal MCAT, and you're solving it for M, so Q over C delta T. You plug the numbers, and then you find your answer, and that is in gram. If you check the units, it's cancel out, and then you end up with gram. And the question is asking about kilogram, so you convert to kilogram, and it's 2.26. Next question, again using QMCAT equation. So you have the mass. Always write down a summary of the information. You have the mass of water, you have the temperature at, it's the initial temperature, so you have the sample of liquid water at this degree temperature is heated up, so that's T1. So T1 is 25, heated by the addition of 145 joule of energy. So you're giving the energy, so the system is gaining energy. So that's a positive Q. So Q is 145 joule. What is the final temperature? So we are looking for the T2 or TF, and C is also given. So again, it's T1 and T2. We have to find delta T. So we solve QMCAT equation for delta T, and that's Q over MC. You plug in the numbers, and your delta T is 5.34, and delta T is T2 minus T1. So you solve it for T2, that's delta T plus T1, and your final temperature is 30.3.